Welcome to this explainer on Chapter 5, Magnetism and Matter. Today we are going to take a journey from the universal, macroscopic phenomena we see every day, right down into the theoretical physics governing atomic materials. I'm super excited to guide you through this because magnetism is one of those invisible forces that feels basically like magic until you map out the brilliant structured rules behind it. Here is our roadmap for today. 1. Universal magnetic phenomena. 2. Rules of magnetic field lines. 3. Solenoids and the dipole analog. 4. Gauss's law of magnetism. And 5. Magnetic properties of matter. Let's just dive right in. Section 1. Universal magnetic phenomena. Magnetism is a truly universal force. We're talking about something that permeates literally everything, from those massive distant galaxies spinning in space all the way down to the Earth itself. Our planet is basically a giant magnet with its own north and south poles, a phenomenon that has been happening since way before human evolution. Section 2. Rules of magnetic field lines. To really understand this invisible force, we've got to map it out. And you can actually do this yourself. If you just sprinkle some iron filings over a glass sheet placed on top of a short bar magnet, suddenly this completely invisible field transforms into a highly visible structured pattern. The filings instinctively arrange themselves, clearly revealing the magnet's distinct north and south poles. Based on those physical patterns, we can lock down 4 strict rules for magnetic field lines. First up, they form continuous closed loops. Second, the tangent to the field line at any given point gives you the exact direction of the net magnetic field. Third, the density of the lines, like how packed together they are, tells you the magnitude or the strength of the field. And fourth, and this is an absolute rule, field lines never ever intersect. If they did, the field would have 2 different directions at the exact same point, which is just physically impossible. Section 3. Solenoids and the dipole analog. Now, if you compare a solid bar magnet with a current-carrying solenoid, you're going to notice something wild. They look almost completely identical. The field lines are practically a perfect match. This brings us to Ampere's hypothesis, which states that all magnetic phenomena can be treated in terms of circulating currents. So that solid bar magnet is actually behaving just like a massive bundle of circulating currents packed together. And here is a huge shortcut for learning this entire chapter. It's like a physics life hack. It's called the dipole analogy. It proves that if you already know your electrostatics equations, you don't need to memorize a whole new set for magnetism. You just swap the variables. Trade the electrostatic constant for the magnetic constant, swap the electric dipole moment P for the magnetic dipole moment M, and change the electric field E to the magnetic field B. The math holds up perfectly. Okay, before we move on, let's pause for a second and test your intuition. Imagine you're holding a standard bar magnet, north pole on one end, south pole on the other. What do you think happens if you snap that magnet directly in half? You might think you'd end up with an isolated north pole in one hand and a south pole in the other, right? Well, actually, no way. You instantly create 2 brand new, smaller bar magnets, each with its own complete north and south pole. So unlike electric charges where you can isolate a positive or negative charge, isolated magnetic poles, known as magnetic monopoles, simply do not exist. Section 4, Gauss's law of magnetism. That unbreakable no monopoles rule leads us straight into Gauss's law of magnetism, which mathematically separates magnetism from electricity. It states that the net magnetic flux passing through any closed surface is always exactly 0. Basically, what comes in must go out. Every single magnetic field line that enters a surface eventually has to leave it to form its continuous loop. So, if we play detective with textbook diagrams, we can easily spot the ones breaking the laws of physics. Lines just shooting outward from a single point? Nope, that implies a monopole, which directly violates Gauss's law. Lines crossing each other? As we established earlier, also totally forbidden by physics. Section 5, Magnetic Properties of Matter. For our final stretch, let's zoom all the way inside the materials themselves to see how they respond to these forces. Down at the atomic level, circulating electrons have magnetic moments. When those moments add up across a piece of bulk material, they create a net moment per unit volume. We call this magnetization, denoted by a capital M. On the flip side, we need a way to measure the magnetic push coming from the outside. That's magnetic intensity, or H. This is the portion of the magnetic field generated purely by external factors, like a current running through a solenoid, entirely independent of the material core itself. So how do we tie the internal magnetization together with the external magnetic intensity? That's where magnetic susceptibility comes in. This is the ultimate metric. It's a dimensionless number that tells us exactly how heavily a specific piece of matter is going to react to that outside magnetic influence. And this susceptibility value beautifully categorizes matter for us. If it's a small, positive number, the material is paramagnetic. It kind of goes with the flow and gently aligns with the external field. But if it's a small, negative number, the material is diamagnetic, meaning it actively opposes the external field. As we wrap up this explainer, I want to leave you with a bit of a lingering theoretical mystery to ponder. We established earlier that all magnetic phenomena are ultimately explained by moving charges, right? Like currents in a solenoid. If that's an unbreakable rule of physics, what exactly is moving inside that cold, solid, totally stationary piece of iron stuck to your fridge right now? Could the atomic world hold invisible, continuous motion we can't even see? I'll leave you to ponder that microscopic mystery. Thanks so much for joining me today.